This is going to be a screencast review of Exam 3 on Chapters 10, Radical Reactions, and Chapter 6, Substitution Reactions for the Spring 2018 Organic Chemistry 1 course. My goal of this screencast is to offer a little bit more strategy in explaining what each question is asking and how to go about solving it. So in the first question, it's asking the reaction between methane and chlorine to give methyl chloride and HCl. So what's happening here is a substitution of hydrogen for a halogen. And this, the only way you can do this is through a radical chain reaction. This is not an SN2 reaction because methane has no good leaving group. To do an SN2 reaction, you have to have a good leaving group, and a leaving group in methane would be hydride or H-, and that's not a good leaving group. So to do a CH substitution, that has to come from a radical chain reaction. The second problem, the reaction between methane and chlorine to give methyl chloride and HCl, is well known. And it's asking you what is the enthalpy change going from the reactants to the products. So you're given this bond dissociation energy chart here, and basically what we're going to do is add up the amount of energy to break a CH bond and a Cl-Cl bond. So we have 105 plus 58, and so we're going to add those together, and that's going to get us 163. So that's the energy that you have to put into the reactants to break those bonds. So the energy given off by forming methyl chloride and HCl in the products. So to form HCl we have 103, and then to form the CCl bond we have 85. So we add these together and we get 188. And so this is actually the amount of energy given off. So we turn that into a negative, and then we add those two together, and you'll see that we come up with D negative 25 kcals per mole. So that's the energy given off through that radical reaction. Question 3, in a competition reaction, equal molar amounts of the 4 alkanes shown were allowed to react with chlorine at 300 degrees. Which alkane would be depleted most from the reaction mixture? So what you want to do anytime you're given a name is draw out the structure. So for A, we have propane, then we have 2-methyl propane. For B, we have pentane. C, we have butane. And D, we have propane. So the next thing you want to do in terms of this reaction is classify the unique number of hydrogen sets and what they are. So you have 2 unique sets, primary, tertiary. For pentane, you have primary, secondary, and secondary. Butane, you have primary, secondary. And for propane, you have primary and secondary. So what this reaction is asking you is basically when a halogen radical abstracts, what is it looking for? And so the most stable radical that can be formed is a tertiary radical. So A is going to be depleted the most because that tertiary radical is going to be formed the fastest. And that's simply from the fact that when the halogen radical is looking to abstract a hydrogen, it's going to do that abstraction from the one that has the lowest enthalpy change for homolytic cleavage. And if we draw it in, it's actually going to be this hydrogen right here. So question 4, what is the product of the bimolecular substitution reaction? So this is going to be an SN2 reaction. So here in our substrate, the bromine is bonded to a primary group, so we have a primary bromide. Sodium iodide is the nucleophile, so we're going to do a substitution of bromine for iodine, and that's going to end up being C. Question 5 is the concept here is that you're going to do a substitution of this bromine for this cyanide. Now the difficulty in this problem is that substitution is happening with retention of configuration. So in a typical SN2 reaction, there's inversion. So you actually have to do a two-step process. You have to invert that bromide, and then in the second step, you're going to treat with the cyanide nucleophile to do a second inversion, which results in retention. So if you were to just treat with A, you would end up with the following product. So that would be the inversion product, but you actually need retention of that starting bromide. So A and B essentially are going to give you the same thing. All you're changing is the counter ion in the solvent. C is not going to give you the correct thing. Even though you're going to do a double inversion with retention, you would end up with the iodide, so D ends up being the correct answer. The iodide displaces the bromine, and then the sodium cyanide then displaces that, so you end up with retention. Question 6 is asking you which of the following best answers the reaction shown. So again, what you're doing here, you're substituting this bromine for this methoxy group to end up with an ether. So you have sodium methoxide. This is going to happen through SN2. So you're going to get inversion of the carbon configuration bearing the leaving group. So the thing about this problem is you have to determine the Cahn-Ingold-Prelog rules for both the starting material and the product. So in the starting material, bromine is going to take priority 1, fluorine 2, this hydrogen 4, and then the methyl group in front is going to be 3. So when you look at, when you determine that, it's going to be, that carbon bearing the bromine is going to be S. So when you do the inversion, the methoxide is attacking from the 100-degree trajectory. Bromine then leaves. You get the inversion, but now you have to still do the Cahn-Ingold-Prelog rules because oxygen is now a lower priority than fluorine. So fluorine is 1, oxygen's 2, this hydrogen's 4, and the carbon in front is 3. So you're still going counterclockwise. That gets you S. So the correct answer for this is A. So you don't want to assume just because you're starting with S that when you do the inversion that you're going to end up with R. You still have to figure it out. In question 7, it's asking you the rank of the carbocations in order of decreasing stability. So 1 is the most stable. Let's just go through and categorize each of these. The first one is a phenyl, and the carbocation, the plus charge is residing in an sp2 orbital. For 2, 3, and 4, the plus charge is residing in a p orbital, which is normal. And then what you're going to do is classify them. So this is secondary, this is tertiary, and 4 is primary. So the most stable is going to be 3 is going to be number 1, so you can eliminate A and D. And then 1 is going to be the least stable, so therefore you can eliminate B, and so the answer is going to be C. In question 8, it's asking you to determine the R and S designation for the starting material in the products and if the product is optically active. So again, what is a Fisher projection? What does that mean? So the vertical line is going back or away from you. Where the bonds cross, that's a carbon, typically a stereogenic center. The horizontal line is then coming out towards you. So go ahead and assign your priorities. So chlorine gets 1, this hydrogen's 4. Now you have carbon and carbon. The ethyl group is actually going to get 2. This methyl group gets 3. So the reason for that is you go out one more and the ethyl group has another carbon. So when you determine what that is, the lowest priority group is going back, so we're going clockwise. That ends up being R in the starting material, so A and D are out. And so this inversion is happening. Here's the leaving group, delta minus, delta plus. Here's our nucleophile. It's attacking from behind, it's displacing. So we can draw the inversion happening about the horizontal bonds. So bromine's now 1, 2, 3, that's 4. The lowest priority group is going away from you, so we determine this is counterclockwise to give S. And this carbon bearing the new bromine here has 4 unique substituents. So yes, it is optically active, and the answer is B. So question 9 is asking you about the nucleophile-electrophile pair to make this thioether. And so let's draw out the bonds from carbon to the sulfur. And so basically you can make this molecule in 2 different ways. So if you're cleaving this bond, you could have this pair. That would be your electrophile. This could be your nucleophile. Or if you're cleaving alternatively the other, this could be your nucleophile. And this could be your electrophile. And that ends up being, if we look, choice A. B is not correct because neither has a leaving group. Neither one has a leaving group. C has the bond polarity for the nucleophile is incorrect. That would actually be ethyl iodide would be an electrophile. Actually, the electrophile shown has oxygen, so there's no sulfur in that one, so that one's kind of your throwaway. And then D is not correct because you would end up with a symmetrical thiol, so you'd have an ethyl and an ethyl. And the product you're after is the ethyl methyl. So question 10 was just asking you to simply look at the attached bond dissociation enthalpies for homolytic cleavage and what is the value for a tertiary CH bond. So 403. So essentially this was primary, secondary, tertiary. So the trend there is that the tertiary is easiest to break, and then you're going to use that information in question 11, where you classify each hydrogen. This is a phenyl. This is secondary benzylic. This is secondary. and this is tertiary benzylic. So this is going to be the hydrogen that's most easily abstracted by a halogen radical because it's tertiary and benzylic. So question 12 is asking you to look at other CH bonds and basically, so here's vinylic, here's aromatic, and here's acetylenic. So the reason that these are much higher, so the bond association energies are a lot higher because you have sp2, and sp hybridized carbon. So it actually takes a lot more energy put into the system to homolytically cleave the indicated bonds. So the correct answer for this one is going to be B. The trend is increasing, and the radical actually ends up in the indicated orbitals. 13 is asking you if one methyl cyclopentane, so the first thing you want to do is draw that out. So you have cyclopentane, you have a methyl group, were to undergo monobromination via radical chain reaction, how many unique types of hydrogen would the product have? So Br2, light. So you need to basically classify the types of hydrogens. You have four unique type: primary, tertiary, secondary, secondary. Bromine's going to go after the most stable radical it can form after it does a CH abstraction. That's going to be the tertiary. And so once that tertiary radical forms, it'll be halogenated. So now you have primary, secondary, secondary. So the answer is A. You have three unique types. So question 14 is specifically asking you about the number of benzylic hydrogens there are in Crixivan, which is an HIV protease inhibitor from Merck Pharmaceuticals. So you need to know what benzylic carbon is. It's the carbon bonded to an aromatic ring. So let's find all those and draw in the hydrogens. So here's one right here that has two hydrogens. Here's another one. So that's 3, 4, 5, 6, 7. So the answer to 14 ends up being C. So 15 is asking you if you were starting with acetylene, what two electrophiles would you use to alkylate the sp hybridized carbon on each side? So basically you're cleaving this bond and this bond, and you're starting from acetylene, which is the following molecule. And the question tells you these hydrogens are acidic. So they have a pK of approximately 25, meaning that if you treat with a base, I'll just say M for the counterion, that's generating your nucleophile. So on one side you need a 3-carbon electrophile. That can be, say, bromine. So automatically you can eliminate B because that has too many carbons in the chain. You can eliminate C because OH is not a good leaving group. So now your choice is between A and D. And so what you need to do in the product is determine the Cahn-Ingold-Prelog rule. So this is the stereogenic carbon. The acetylene carbon is going to be priority 1. The ethyl is priority 2. The methyl is priority 3. So in this sense, in the product has this configuration of R. So in an SN2 reaction, we know that inversion occurs, so that must mean we have to start with the S. So that means you're going to start with 2-iodobutane. So S2-iodobutane plus propyl bromide. The choice is D is going to be the most appropriate. So in question 16, it's asking you the ratio of monobrominate to isomers from the radical bromination of 2,3-dimethylhexane. So again, just draw out that structure. So we have 1, 2, 3, 4, 5, 6. So 2, 3 dimethyl. Then go through and basically what it's asking you is what are the unique sets of hydrogen. So the 1 and 2 methyls are equivalent. So there's 6. You have a hydrogen at 2, that's 1. Hydrogen at 3, that's 1. The methyl group at 3, that's 3. The methylene at 4. The methylene at 5. And the methyl at 6, so this answer is going to be B. So that's just asking you the ratio. Then you can consider the classification of each of those in terms of which proton or radical, halogen radical is going to abstract. That gets to the heart of question 17, and the answer for this one ends up being A, which is 3. So basically, if you classify these from the above question, you have methyls, primary, tertiary, tertiary, primary, secondary, secondary, primary. So again, a tertiary radical is going to be the one that's most easily formed. And so you have 2 of those. So we've drawn 1. So there's the second one. We recognize that this is now a chirality center. So we have 2 to the n. So this actually ends up being 2 because you can generate an R or an S for that stereogenic carbon. Question 18 is asking you about a reaction coordinate diagram, and basically at what point along this coordinate is a carbocation intermediate. So the top of this curve, so points A and C, those are transition states. And anytime you go down into, say, a well, that's called an intermediate. And why is it intermediate? Actually, because there's some residence time in that well. When you're at the top of this peak in a transition state, you can only go down from where you came or down towards product. When you're in the well, you can reside in that well for a little bit longer residence time. So again, the answer for this is B. Considering the reaction coordinate from the prior problem, points A and C were transition states, and the free energy of the reaction was overall negative, so it's exergonic, meaning that heat is given off. So question 20 is asking you basically to look again back at that table and consider how much energy would be required to remove a proton, knowing that in this molecule all of them are the same, they're tertiary protons, so the answer is D. Question 21 is asking you about an SN1 reaction, so unimolecular substitution. And again, that proceeds through a carbocation. And if you had 4 of these starting materials in a flask, which one would go to the product the fastest? So you have to characterize the starting leaving group. So this one's bonded to an sp2 hybridized carbon, so that you know that's going to be the slowest. It's not going to happen at all. This bromide is secondary. This is secondary allylic. And this is secondary. So you have B, C, and D are all secondary, but C is special because once it ionizes, so what do we mean by that? You have delta minus, delta plus. This ionizes. Bromide leaves, so minus bromide. You now have this allylic carbocation that's resonance stabilized. So question 22, you're asked to form phenyl propyl ether. First things first, just draw it out. So there's phenyl. There's our propyl, that's phenyl propyl ether. Now you're given choices. C and D are off right away. Why is that? They're bearing halogens, so they would be the electrophile. But the issue is that electrophile is bonded to an sp2 hybridized carbon, so they're no good. That leaves the sodium phenoxide as the nucleophile for A and B, so either of those choices is appropriate so far. But when you look at now the electrophile, which is over the arrow, OH is a bad leaving group, bromine's a good leaving group, so this answer is B. So that again, that's an SN2 mechanism. So in question 23, we're asked about the unimolecular substitution reaction of the substrate. So it's SN1, and again, that tells us it's going to proceed through a carbocation. Let's go ahead and draw out that name. So we're starting with a pentane, and it has some stereochemistry. We have 2-chloro-3-methyl. So let's go ahead and draw in the 2-chloro with the R, and the 3-methyl with the S. So it says this is hydrolyzing, so you need to form that carbocation through ionization. So this is ionizing to a secondary carbocation. And then what we need to do now is recall the carbocation stability trend. So we're starting with secondary. We know that tertiary is more stable. We look next door and we actually have a tertiary carbon, so we know we can do a hydride shift. So once that happens, now we've lost all stereochemical information in this molecule. The first ionization destroys the 2R. The hydride shift destroys the 3S. So this is achiral. Since we're in water, which is a weak nucleophile, when this gets trapped, we're forming D3-methyl-3-pentanol. There's going to be no stereochemical information, so A and B are out. There's no base present, so C is out as well. Question 24 is asking you which of the following nucleophiles best matches this IR spectrum. So notice this broad OH peak at about 3400. The 1800 region indicates no carbonyl. So if we scan with the list of choices, A has no OH. Sodium bromide would not look like this in an IR. C is acetic acid that has a carbonyl. So we can eliminate that, and then the correct choice is D, ethanol. So the final question, 25, is asking you about the number of radical intermediates that are present in one methyl cyclohexene. So there's one methyl cyclohexene, and basically if a radical halogen were to abstract from an allylic position, so first identify the allylic positions. So this is allylic, and that's allylic. So once you form radicals there, them being allylic, they can have a hybrid form. So since there's 3, you're going to get 6 total. So let's go ahead and draw those out. Again, be logical about how you go about doing this. So here's a radical. Here's a resonance form. And then the last allylic radical. So what implications does this have on a reaction? You could potentially get up to 6 different products. So that's the concept that's being tested here.